Okay, so this is a continuation of the screencast that I posted earlier about two-way analysis of variance with replication. And in the first situation, we basically had a situation where we were looking at two-way analysis of variance where the interaction was not significant. So we had rats that were fed on different kinds of fat, and the main effect that was significant was the difference between the two types of fat that they were fed, with no difference between male and female. You see down here that the fat types are in the columns, and the sum of squares due to columns is huge. And when that appeared in the analysis of variance, that was the only feature that was significant. So what I've done in the next section, just to illustrate to you what an interaction looks like, is I've just taken the rancid data for males and interchanged it with the fresh data for males, so that I'm just going to take this column, place it where this is, put this column where this is. I'm not going to do anything to the female data. So this is not the original data. It's me manipulating the original data to illustrate a point. So when we look at it now, we once again have the same means that we had a few minutes ago, 535.33 and 695.67, but now all I've done is just switch those around. So the row means don't change at all, and so there still shouldn't be a difference in the overall mean of males and females. And when you look up here, it's still 615.5 for males, 580 for females. And when you look down here, it's still the same. But what does change is the sums of squares, or the column means for the fat type. So you have 589, 606.5, as opposed to what it was before, which is 669 and 526. So we've just rearranged the data a little bit. But everything happens in the same way. You basically calculate the grand mean by adding up all of the values, and it should be still 597.75, and you see still 597.75. The subgroup means are going to be the same, 65,903.58. And the reason for that is that you still have the same subgroupings. It doesn't matter whether they are associated with male and fresh fat or male and rancid fat. These means, this mean here, this mean here, this one here, and this one here, they're all still the same. And so when you subtract them from the grand mean, you still get the same sums of squares for subgroups. In addition, the sums of squares within are the same. They've just switched places. So there was 6738.67 here and 466.67 there. Go back to the previous example, we've just flipped those. But once again, the total of the sums of squares within is still 11,666.67. So the sum squares total is still the same. It's the subgroup sums of squares plus the within sums of squares to give you 77,570.25. The sums of squares row should not change because we didn't change anything with rows, so that should still be the same as it was earlier. And we see there that it is, just follow my pointer. But the sums of squares column is now 918.75, which is the difference between this column and the grand mean and this column and the grand mean. That has sunk to 918.75, and the interaction term is now huge. And so when we look at the ANOVA table, if we transfer these values over to the ANOVA table, we once again see this one down here. The one at the top is the one that has a significant interaction term. We see that large sums of squares for the interaction divided by 1 gives you a large mean squared for the interaction, which divided by the error term is a large F statistic. And so we've basically, by moving those two columns, we've taken the variance that was due to column, and it's now being partitioned out as part of the row by column interaction. As a result, column, which was the effective fat type, is no longer significant, just like rho was not significant before. All of the variation in the data is due to, let's go back, it's all due to males with fresh fat and females with rancid fat having similar growth rates, whereas females with fresh fat and males with rancid fat have higher rates of growth. So the response, which is growth rate, varies not just by fat type, but by a combination of both fat type and sex. So it's the interaction term that becomes the significant term in the overall two-way ANOVA. So when we graph this, it looks like this. For females, they grow best with fresh fat, but they grow less with rancid fat. Males grow less with fresh fat and more with rancid fat, so that the average from fresh to rancid essentially cancels one another out. The average of this value here with this value here is somewhere in the middle. The value of this value here and this value here, their average is somewhere in the middle. So there's no effect of fat. And in the same way, there's no difference between male and female because the average of male under fresh with male under rancid is somewhere in the middle, and the average of female under fresh and female being fed rancid is somewhere in the middle. So there's not an independent effect of sex. So when we look at the rho effect, which is sex, it is not significant. When we look at the column effect, which is fat type, it is not significant, but it's the interaction that is significant. So for this situation, we had fat type, which was fresh and rancid. We had sex, which is male and female. There are only males and females among rats, and the researchers were only interested in fresh versus rancid, and so we would treat both of these as fixed effects rather than random effects. We talked before spring break about the difference between fixed and random effects. Fixed effects are where your experiment contains all of the levels of that variable that you might be interested in. In the case of sex, it contains all of them because among rats there are only males and females, and among fat types there may be other fat types, but these are the only two fat types that are of interest to the researchers. These aren't a random sampling of a variety of fat types. And so in your textbook, there is a figure 911, or table 911, that basically shows you how you calculate F statistics under fixed and random effects. If A and B are both fixed, it's always just the mean squared of whatever the effect is divided by the mean squared residual. So you would divide the mean squared residual into the effective row and column and the interaction. If both of them are random, you don't divide it by the residual, you divide the main effects by the interaction effect, and you divide the interaction effect by the residual. If A is fixed and B is random, you divide the fixed value by the interaction term and the random value by the residual term and the interaction term by the residual term. Same way, if well, there are two versions. The restricted version is the version that we're going, the unrestricted version is the version that we're going to pay attention to, where you basically divide your main effects by the interaction term and your interaction term by the residual. So this is how you would calculate F statistics for evaluating whether the main effects and the residual effect is significant. And so in this system here, since we're treating both of these as fixed effects, all of these mean squares are calculated by dividing, or all the F statistics are calculated by dividing the mean squared of row by the error, mean squared column by the error, the row by column interaction by the error to get these F statistics. And that's where we will leave off, and hopefully we'll get through these two things on Wednesday.